Hello, thank you for having me, and sorry that I can't be there in person. Really appreciate the invitation, and today I wanted to tell you a little bit about building physical intelligence. I'm a co-founder and CEO of Physical Intelligence. So unless you've been living under a rock, over the past few years, you probably noticed that something happened in robotics. So the robotics that we are used to looked more like this, where we have robots that can do very repeatable tasks, go from A to B very well, very fast. But as soon as we introduce a little bit of lack of structure, they would very often result in something like this, where the robot was not able to deal with the chaos of the world and the unstructured environment, and it would basically catastrophically fail. But then it seems like something happened, and right now robotics looks very different. It looks more like this. We see extremely smooth, impressive dance moves from many different humanoid robots. And we see robots deal with unstructured environments like this one just fine. So the question I want to answer today is, well, what happened? Right? There seems to be a very big difference between the robotics of the past and robotics of today. So over the past year, I've been building physical intelligence, and I've been building it in two different ways. On one hand, I started a company called Physical Intelligence. We started around a year ago with the idea that we want to build a model that can control any robot to do any task, truly solve physical intelligence. On the other hand, I also had a daughter who is around 1 year old today. So I experience emergent physical intelligence almost every day these days. And if I were to draw a conclusion from these two things, is that if you're thinking of starting a company and having a baby at the same time, please talk to me. I do not recommend that. Don't do it. All right, so back to the question, what happened? I think the very obvious answer is, well, AI happened. And there's many different versions of this answer that actually matter here. But I think the one in particular that has been really, really important that I want to focus on is vision language action models. So let me tell you a little bit more about them and why I'm very excited about them. So how do they work? They work fairly similar to vision language models that we know from products like ChatGPT. So in a vision language model, the way it works is that it takes some data from the internet, for instance, an image that you can find on the internet, an image of a cat. Then you can ask it, what is this? What do you see in the image? And then this model is trained to answer it in natural language as well. So it would answer with the word cat. Now, it turns out that we can take that model, this vision language model, and adjust it a little bit to be practical for robots and actually really, really powerful for them. So the way it works is the following. We'll take a vision language action model now. And instead of having an image from the internet, we would have the camera feed from the robot. So what the robot currently sees. And instead of asking it a question that you can answer in natural language, we'll ask it to do something. We'll ask it to do a task, like fold a shirt. Now, given that that model has also seen robotics data, and in particular data from many different robots doing many different tasks, it turns out that it can output an answer that tells you how to do the task. So it actually outputs motor commands for the robot to do the motion to accomplish that task. Now, it's a very simple idea. It's basically a vision language model adjusted to deal with robotic data. But it turns out it's really, really powerful. So why is this so powerful? Why is this a big deal? Well, traditionally, that kind of thinking where you can train the model fully end-to-end that can understand what the robot sees and output the correct actions has been really hard because these models require a lot of data. But with this idea, with the idea of vision language action model, it turns out that you can collect data from many other sources. So one, you can connect data from the web. In the past, we thought that to make a model like this work, you would need to have a robot experience the entire world firsthand. It would need to experience every single object, every single situation to learn about it. But then it turns out that you can take a pre-trained vision language model that was pre-trained on the web data and has some high-level understanding of how the world works and transfer some of that meaning to robot motion. And one particular result that I was an author of that showed that that actually doesn't look that impressive, but it was completely mind-blowing to us, was from Robotics Transformer 2, showing the following. This is a robot being asked to move the Coke can to Taylor Swift. Now, I'll show it to you again. Watch closely. The robot picks up a Coke can and moves it to the picture of Taylor Swift. Doesn't do a great job. The Coke can falls. You can see that it's kind of pathetic. But to us, watching this experiment live, that was a very, very big deal. And the reason is that the robot has never seen pictures of Taylor Swift. It's never seen any pictures of any of these celebrities or any other pictures. It had that abstract concept of who Taylor Swift is and what the picture of Taylor Swift looks like straight from the internet. So it was able to get that knowledge from web scale pre-training and then translate that knowledge and connect it to robot motion to actually express that understanding through an embodied movement. So that for the first time showed us that it's actually possible to get all of that knowledge, not firsthand. The robot doesn't have to experience the world, every single situation in it. It still needs to experience quite a bit of it, but it can get a lot of that understanding from the internet instead. So that was one. The second one that made it really, really impactful is the fact that not only we can connect it to the data from the web, but we can connect it from data from other robots. So it turns out that these models don't really care whether it's all the data comes from a single embodiment or many different embodiments, or a robot that has one arm or two arms, or it's a mobile robot or a drone. It doesn't really matter. At the end of the day, it's a pattern of numbers and pattern of different data that these neural networks can find and can understand well. So to do this, we run an experiment called RTX, where we collaborated with many different research institutions around the world, 34 of them, and asked them to send us the most recently collected data sets that they used to publish their research. Now, if you've done academic research, you know that the way it works is you collect the data set, and then you try to get your method that you're about to publish really, really work. And you're very heavily incentivized to get it to work because that's what you want to publish. So we took all of those data sets that were published for different methods, and we combined them into one big data set and trained one big generalist model on that. So that was trained on many different robots that look different, that have different number of degrees of freedom. Sometimes it's two arms, sometimes it's one arm. It doesn't really matter. And then we send the checkpoint of that model, of that generalist model, to these individual labs and ask them to compare it to their state-of-the-art method that they just developed. Now, importantly, it's a different state-of-the-art method in every single lab, because every single lab developed a specialist solution for the problem that they were trying to publish on. And then it turned out that as a result, our generalist model was able to beat that baseline, that state-of-the-art method, every single time, on average by more than 50%. And that points to the fact that these models are really data hungry, and they can make sense out of data coming from many different embodiments, and then can do it much better than we can. So with these two, we decided that this is a technology that would allow us to build a model to control any robot to do any task. And that's where we started physical intelligence. Now, the way we want to do this is to build a generalist model that will be trained on many tasks and many robots, with the idea that we'll be able to generalize beyond that. In particular, it will be a generalist vision language action model that will be trained on many tasks and many robots. Now, as we started that journey, we thought that there's going to be three big challenges that we really need to de-risk and understand better. These are capability. Are these models capable of doing tasks that we've never seen robots do before, that are very dexterous, long horizon, and so on? Secondly, generalization. Can they generalize to an extent where you can put them in a completely new room, in a completely new environment, and they know how to do it? And then third, performance. Can they perform at a very high clip with very high success rate and be extremely robust? So we started with the first one, capability. Around 5 months into the company, we arrived at these results. This is a demo you might have seen, showing one of our robots unloading a dryer, taking all of the laundry into a basket, bringing it over to a folding table, and then folding it one by one. You can see that it's not perfect. It makes quite a lot of mistakes, but it can correct basically all of them. It's still fairly slow. It doesn't work every single time. But this is a task that for a very long time has been considered a holy grail of robotics. This is something that we've been able to achieve 5 months into the company. And this is not a model that is specialized in this particular task. The exact same model could do laundry folding like the one you see. Could also work on static robots, whether it's single arm or 2-arm robots. It could also work on different mobile robots and do many, many other different tasks. So I wanted to tell you a little bit about what we did to make it work. So we trained this generalist robot policy. We call it BAAI0. This is our first model that we released in October last year. That was pre-trained on many different robot form factors that you see here on the left and across many, many different tasks. Now, we also use a pre-trained vision language model to get that internet scale pre-training that I talked about earlier, as well as the open data sets, open source data that I talked about as well. And then from that, we built a single architecture, single vision language action model called BAAI0 that has an action expert that allows it to actually output actions. Now it can do multiple things. First, it can work zero shot, where you can just prompt it, and for tasks that it's seen before, it can perform them fairly well. But you can also fine-tune it. And you can fine-tune it with what we call post-training, that is much higher quality data, which allows you to do two things. One, it allows you to kind of specialize this model for tasks that are particularly difficult. So for something like laundry folding, it's not enough to just pre-train it. You kind of need to fine-tune it to tell it how exactly you want your clothes to be folded. But you can also use it to train new tasks very, very quickly. So before I tell you a little bit more about the architecture, I wanted to kind of have you appreciate a little bit how hard of a task it is. It seems like folding laundry is not that difficult. We do it every other day or so. But it turns out that it's actually quite tricky. So here are a few examples. The same model running on static robots. So you can see this is a problem where you find a shirt that is in arbitrary configuration, and you see how many different motions you need to do to grab the corners correctly. You can see that the robot eventually grasps the sleeve correctly. It kind of flattens it out a little bit. Once it's done, then it grasps the corner well, then it folds it in half, brings the shirt a little bit closer to itself, folds it again, then folds it in half, then straightens it out. That also takes quite a bit of work. And then it does this beautiful dynamic motion to folds it one more time, brings the pile over, and puts the shirt on top of it. Here's another example with a piece of clothing that the robot has never seen before. So you can see that the shirt is in some weird configuration. The robot tries to flatten it out, and it realizes that something is off. It tries it few times, and then eventually it figures out that it actually didn't grasp the right corner. So it needs to put it down, grasp it again, grasp the corner correctly, then brings it over, folds it in half, folds the other half, and then eventually is able to straighten out the shirt to the final dynamic motion at the end and puts it on a pile of clothes. In fact, the system is robust enough so that you can interrupt it, and it can handle these interruptions quite well. So here's a robot minding its own business, trying to fold the clothes. And then one of our researchers, Michael, is putting another shirt and trying to mess with it. And you can see that the robot kind of realizes what's happening, puts the shirt back, and kind of tries to do its job. This is not something that we train specifically for. It's just something that emerges from large-scale training like that. You can also mess with it in other ways. Here is a robot trying to fold a shirt in half, and while it's kind of halfway through, Michael comes in, our mean researcher, and unfolds it. So then the robot starts again and starts with the other half, and Michael comes in and undoes it again. Now you can see that one of the corners is a little bit off, so the robot needs to figure that one out. It finds the corner correctly, and then eventually folds it and keeps on going. So this is what these models are capable of. But the most if I were to distill it into one insight that was really, really important to get it to work, is the insight of pre-training and post-training. And what I mean by this is the following. So for BAAI0, we had pre-training data that consisted of 10,000 hours, so many different tasks across many different robots, where in that phase, we try to cramp as much data into the model as possible, very similar to the pre-training stage for large language models. But then we would go to the next stage called post-training, where we would collect orders of magnitude less data of high quality, around 20 hours of data, to kind of get this model to behave exactly like we wanted. So kind of pick the mode of behavior that we actually meant. We can do this for laundry folding. We can do it for building boxes or for many, many other tasks. And that turned out to be really, really important to get it to work. So in particular, to give you some quantitative evaluation, we can compare 3 different approaches. We can compare the approach I just described, where we do pre-training and then post-training. We'll be comparing it to an approach where we have no robot pre-training, so we just train on this curated data set of really, really good high-quality data. And we'll compare it to an approach where there is no post-training, so we just train on all the data and that's it. Now, here are the results. So if we do both pre-training and post-training, we see the highest number. This is where we can get really far in this folding task. Because it turns out that you kind of need both to first understand the motions of how to deal with all kinds of different situations, which you get from pre-training. And then you need post-training to really fine-tune those motions, to get it to really the result you want. Now, if you don't do any pre-training, if you just do curated data set, it turns out that the performance drops significantly. And the reason for that is that you know how to fold things perfectly, but the real world is not perfect. You're going to fail, you're going to make mistakes, and you don't know how to deal with that diversity, how to correct those behaviors, because you've never seen that situation. You've only seen perfect data. And then lastly, if you didn't apply any post-training, that means you know more or less how to fold clothes, but you don't really know what exactly we want. And that also drops in performance quite a bit. So now one question you might ask is, this is a generalist model, right? That's not just a model used for laundry folding or building boxes or many of the other tasks I mentioned. It was also trained on many other robots. So can you use it? Can anyone use it? And the answer is yes. We open source that model. We open source it in a repository called OpenPy, where we open source many different checkpoints of it. We also show different robot runtimes, how you can integrate it into your framework. And we have many, many people using it, fine-tuning it on all kinds of different applications, ranging from robotic surgery to autonomous driving to many, many other tasks. In addition to this, we also started a partnership program. Here's one partnership video with Astrobot humanoid robot, showing a robot making coffee. And you can see it being a robot that is more complex. It has many more degrees of freedom. It's kind of harder to control because of that. But we can take a pre-trained BAAI0 model and fine-tune it to a new embodiment like this and do a task that is fairly dexterous, that the robot can perform fairly well with this generalist policy. All right. So since I mentioned humanoids, I wanted to spend a few more minutes on humanoids. You've probably seen that the world went crazy about humanoids. There's many different humanoids. There isn't a day where you don't hear about a new humanoid being developed. There's many different companies making those robots, amazing pieces of mechatronics, robots that will be capable of many, many things. And we've seen all kinds of different applications and demos of these robots, whether it's in the home or in some kind of structured home environment where they're collaborating and doing fairly dexterous tasks. Now, I believe that if we actually succeed, if we actually crack the problem of physical intelligence and build these models that are extremely general, I don't think we're going to stop at humanoids. I think we're going to experience a Cambrian explosion of robots. Because let's be honest, if you wanted to do something like sort packages, you wouldn't be doing it with a humanoid if you wanted to automate that. If you were to automate it, you would want to do it way better than humans. You would do it with a robot like this. And that turns out to be true for many different applications. You can do much, much better than humans can, because it's not our form factor that makes us special. It's our brain, our physical intelligence that makes us special. So we can see all kinds of different robots being applied to many different domains. And I believe all of them can be powered by a single generalist model like BAAI0. So for instance, if you want to do roofing, you'll use a very different robot. If you want to do some kind of self-assembly or space exploration, you'll use very different robot. If you want to do firefighting, you'll use very different robot. If you wanted to do agriculture, you'll use a different robot. And if you wanted to do recycling, you will use a very different robot. And there's many, many more applications where there's way better form factors that are superhuman in some way, but they can be powered by the same general brain. All right. so sorry about the small digression. I talked a little bit about capability. So next in our journey, we tackled generalization. So one caveat about all the demos you've seen and you see day to day about robots is that they're always evaluated in the environment that they've been trained in. So the demo that I showed you earlier in a home where the robot is folding laundry, if I were to bring it to your home, it probably wouldn't work. It hasn't seen that home. And this is one of the big bottlenecks that prevents us from deploying these machines. So as the next step, we wanted to tackle that problem and get robots to generalize to a completely new environment they've never seen before. And it turns out that it's possible. So this is a project we call BAAI2025.
Did you clean the bedroom?
Where we bring robots to completely new homes that they've never been to before. So this is a new Airbnb that we rented in San Francisco. And here's our researcher, Laura, asking it to clean the bedroom. The robot has never seen that bedroom before. It starts putting the clothes away, then it puts trash in the trash can, and then it makes the bed at the end. In fact, all our evaluation in that work has been done in completely new environments that the robot has never seen before. So we're literally driving around San Francisco, assembling the robot and putting it in environments it's never seen before and evaluating it only there. Now, the most important quantitative result from that work is this. And this is a plot that I've been waiting for a very, very long time. So let me describe a little bit what it shows. Here on the x-axis, you see number of locations that the robot was trained on. So the robot has seen many different homes, and the x-axis is how many homes it's seen in its training data. Now on the y-axis, we see the average task progress, so the task performance, and this is in a new home that the robot has never seen before. Now you see here this yellow line shows you the performance in this unseen location using our method, our BAAI2025 model. And it turns out that the performance goes up and up the more homes you've seen in your training data. And by the time you've seen 100 different homes, if you go to the 101st home that you've never seen before, it turns out that the performance is very high. It's over 80%. Now you can also compare it to a situation if you had data in that environment. So if you just came into that home, collected data in that home, what is that performance? And this is what you see in this bar that is in green. So this is if you had in-domain data. So it turns out that you can visit around 100 homes, and by the time you go to the 101st home that you've never seen before, your performance will be similar in that never seen before home to the situation as if you collected data in that home. And this is something before we started this project was extremely unclear. Some of us thought maybe you need to visit 1 million different homes to be able to generalize that way. It turns out that around 100, you're able to basically get that performance. Now, two other really important caveats here is that if you don't use pre-training that I talked about before, the performance drops significantly, even if you use in-domain data. This is the light green bar. Now, if you train on all the 104 locations and don't use pre-training, the performance plummets even more. And this speaks to the power of models that are very general, that are trained on many data sets across many different robots in many different situations. They develop better understanding of the world, and they can actually work in environments that they've never seen before. So at this point, I would say that we know that these models are capable of incredible things that we've never seen robots do before. We know that they can generalize to environments they've never been before, like homes, the most diverse environment there is. The last question is, can they perform really, really well? All the demos I've showed you, they work some of the time, sometimes 80%, sometimes 90%, sometimes less, but they don't work every time. And if we really want to deploy this technology and bring it to the world, they need to be working 100% of the time, be extremely reliable. I'm not going to tell you about this yet, but please stay tuned. There's more to come on that axis as well. All right, so to summarize, where are we at and what's still missing? I would say the following. We have a prototype of a generalist model that can be trained on many different robots, many different tasks, a true generalist. And I think it shows kind of sparks of physical intelligence. It's not the physical intelligence that I imagined yet, but I think it's starting to get there. It starts to work on new robots. It's starting to work in new environments. It starts to do tasks that we've never seen robots do before. It shows some really interesting behaviors. And then even more importantly, we're starting to develop this recipe for training these robot foundation models. a recipe that you can apply, a recipe that we understand a little bit better, that is more repeatable, and that many others can apply as well. Having said that, we are still very, very early. There's lots of things that are missing. First, we are not yet there when it comes to generalization. I showed some signs of really impressive generalization, but if you compare it to something like large language models, we are not there yet. Secondly, we need to get these models to be much more robust and much more performant. As I mentioned towards the end, this is something that we're working on, but we're not there yet. It's unclear how long it's going to take to get us fully there. And then lastly, we also need to understand them better. We need to understand the recipes, we need to understand the scaling laws, we need to turn it into a science similarly to what happened with language and vision. We need to have scientists kind of start to poke at these artifacts and understand how to build them better. Now, at the very end, I wanted to leave you with how I think about this, how it's going to transform the world. If you think about electricity that we developed a long time ago, initially when humanity was working on electricity, it seemed like it would always require so much effort to get it. It seemed just insurmountable to get it to a place where it's available to everybody. But now when you think of electricity, it's available at the flip of a switch. And I think something similar is going to happen with labor. Right now, labor is kind of the clock speed of the world. It's something that takes a lot of effort, and it's very, very, very difficult to get. But I think if we're successful, if we solve physical intelligence, labor will be available at the flip of a switch. Thank you.